Hi. In the last video, we defined the law of conservation of energy. And in this video, what I would like to do is I would like for us to use a tool to help us make sure that we abide by the law of conservation of energy. Okay. And it's going to be a visual tool. So we've titled this section Visualizing Conservation of Energy. Now, there's two ways that we can visualize energy as a phenomenon happens. Okay, we could use pie charts or we could use bar graphs to help us visualize what energy a particular system has, especially as that system changes over time. Okay, so here's a great example. Here we have a ball that is held above the ground and then it drops so that it falls straight down. And we've got three different parts of this motion that we're going to be interested in. We're going to be interested in right after our hand leaves the ball. We're going to be interested at some time during the fall. And then we're interested in the moment before the ball hits the ground. And I'm going to number these things. I'm going to number it maybe like 1, 2, 3, because what we are going to do is we want to think about what energy is present in the ball at those three different snapshots of the motion. So what we need to do is we need to think about, the four different energies and whether or not they're present. So starting with the first snapshot where we have just let go of the ball. We know that when we just let go of the ball, it will not be moving. So we would not expect to see any kinetic energy. This ball is at some height above a surface. So we would expect to see that there is gravitational energy in this ball because that's the definition of gravitational energy, right? It's an energy of a location above a surface. There's no deformation that's going to happen during this motion, so we would not expect any spring energy, and we're just going to ignore any kind of thermal energy that we have right now. Mostly because the only way that we could calculate it would be to think about friction, and we're going to ignore friction in this problem. So the only energy that this ball has at location 1 is gravitational energy. Now, as it falls, it comes to a lower height above the surface. So because it is at a height above the surface, we still expect it to have gravitational energy, but we do expect that gravitational energy to be less due to the fact that the height above the surface is less. So we have this amount of energy then that had to become a different type of energy, okay? Because we cannot get rid of this, right? We can't just spontaneously lose all this energy. That would break our law of conservation of energy. So what energy might it have become? Well, when we are down here, we are now moving, and we know that moving is associated with kinetic energy. And we still have no deformation. We still are not going to concern ourselves about friction. So we would say that all of the gravitational energy that we previously had that is no longer gravitational must have all become kinetic energy. And then by the time we are directly above the ground, we're like a millimoment away from hitting the ground, then we are practically on the ground and all of our energy must be kinetic energy, right? All of our gravitational energy is gone. And so pie charts are really useful for us visualizing how the energy is changing throughout a particular motion, right? We started with all gravitational. That gravitational then became less as our kinetic energy increased until by the end of the motion, we had nothing but kinetic energy. Now, graphs can show this as well. They can be very useful, and some people prefer a bar graph as a way to show what the energy is doing. Uh, And so I wanted to familiarize you with them. So on a bar chart, we need to have labels on our x-axis. So I gave us kinetic, gravitational, spring, thermal energy. And a bar graph is going to still show where the energy is, but just in a slightly different way. So at the start, we had nothing but gravitational energy. And then partway down, our gravitational energy decreased. So I now only have 3 boxes of gravitational energy. And the remainder went to kinetic energy. And then at the end here, all of my energy ended up being kinetic energy. Now, bar charts are a little bit more time intensive to draw because you have to draw the axes, you have to draw the labels, then you actually have to draw the bars themselves. Pie charts are faster to draw. And the advantage of pie charts is that the pie is always going to add up to 100%. So we're always going to maintain the same number of joules with a pie chart. Whereas with a bar chart, we have to make sure that we are keeping the same number of boxes on our chart throughout the different snapshots. So I had 4 boxes and I got to make sure that I have 4 boxes on all of these graphs. So it's a little bit more bookkeeping than a pie chart. So you'll notice that in this class, I'm going to be using pie charts, but I wanted to make sure that you were familiar with bar graphs because lots of other people prefer them instead. Okay. Now, why would we want to perhaps do this? Why would we want to have these visuals? Well, it's because when we are asked questions, we may be asked a question like a ball starts 16 meters above the ground, and I want to know how fast it's going to hit the ground. Well, we can use the energy to solve that problem, right? Because if I take a look at the energy that I have when it's 16 meters above the ground, I can then set it equal to the energy that I have when it hits the ground or is incredibly close to hitting the ground. And I can solve the problem that way. So I can set my energy at the start, which is just gravitational energy, equal to my energy at the end, which is just kinetic energy. And since oh wow, don't do that. Since I know that gravitational energy is mg delta y, and I know that my kinetic energy is 1/2 mv squared, I now have set myself up with an equation where I can substitute in numbers and start to actually solve for information. Okay, so that's why we like to do these pie charts. These pie charts are here to assist us in writing a little energy equation. All right. So let's do a couple more examples of these pie charts so that you guys can be able to put this stuff together really fast. So a wind-up toy is wound up and then walks across the table and comes to a stop. So at the very start, since we wound up this spring, we're going to be we're just going to consist of nothing but spring energy, right? We deformed that spring, and that's where we've stored the energy. Now the spring is going to unwind. Oops. The spring is going to unwind, and so we will still have some spring energy, but it causes the bunny to start walking. So we are also going to have some kinetic energy due to the motion. And if you've ever played with any of these toys, they're really loud and they have a ton of friction. So we're going to be losing energy to heat, light, well, not light, heat and sound. So we're going to have thermal energy in there as well. Okay, so that second position actually has a ton of different energies associated with it. And by the time the little wind-up bunny stops, it will have stopped because all of its energy has been dedicated to, heat or sound. Okay, friction has caused it to all become thermal energy. Let's do a super ball is dropped and bounces up and down. So if we look right away, we drop it. So there's no motion, no kinetic energy, but we are far above our surface. So I'm going to expect that this is all gravitational energy here. Then it comes, it hits the ground, or at least it is a millisecond before hitting the ground. So a millisecond before hitting the ground, we will have changed all of our energy from being gravitational to being kinetic. Then it rebounds, and if you notice, it rebounds up into the air, so there will still be gravitational energy. However, you should notice that it didn't rebound as high as it did originally. So that tells us that there's more than just gravitational energy in this ball. Some of it must have been lost to maybe perhaps heat. So there is some thermal energy here. And that thermal energy does not change, right? Just because we fall, we still had dedicated a whole bunch of energy to heat, and that heat is not coming back out of the object. So that stays the same, and as we go back to the ground, change all of our gravitational energy to kinetic energy, right? To that motion. And then notice we rebound again, less high than before. So that tells us that our thermal energy must have increased again. Oops. So on our rebound, yes, we do have gravitational energy, but notice that this is even smaller. It's an even smaller component of our pi. And that helps us understand why this thing rebounds at a lower and lower height every single time, right? Because more and more of our energy is becoming thermal energy. Okay. And then lastly, we've got an object rests on a coiled spring and then is launched upwards. So we've deformed our spring, but nothing else is really going on. So we would expect that all of our energy is spring energy. Then we let it go and our spring uncoils. So now none of the energy is going to be spring energy. Instead, the object gets launched into the air. So we would expect that we would have some gravitational energy associated with going up, up, up above the ground. And we are moving as we go up, up, up above the ground. So we must have kinetic energy because kinetic energy is that energy of motion. And when we get to the top, right, we know that at the peak of motion for a projectile, we stop. So we no longer have any kinetic energy at all. Instead, all of our energy ends up being gravitational energy. Okay. And like I said, why are we making these pies? Well, we're making these pies so that we can quickly be able to write a little energy equation. So if we wanted to say like, hey, there's something, we got some information about this bunny at the start and about partway through its motion, what we could do is we could take the energy pi of the start and set it equal to the energy pi partway through the motion. So US plus U thermal plus kinetic. Okay, and I mean, really this occurs, or this works for any of these, right? If we just take the energy pi of whatever we're interested in at the beginning and then set it equal to the energy pi of whatever we're interested in at the end. And same thing here, right? We could do the beginning and we can do the very end. So I would take my energy pi at the beginning and set it equal to my energy pi at the end. And from there, I can actually now solve any word problem. And we're going to look at some word problems in the next video.